All right, welcome to our next recording in molecular and cellular biology. And today we're going to talk about atoms and elements in our chemistry review. Again, this is the highlights of the chemistry chapter from your textbook. And today we want to talk about atoms, structure of atoms, and elements. Atoms ultimately are the stuff that make up everything. So when we talk about matter, we're talking about things that are made of atoms. It's the smallest unit of matter that has the characteristics of that particular kind of matter. And each kind of matter that's out there is called an element. Think about it as flavors of ice cream, right? So you can get all different kinds of scoops of ice cream. They're all scoops of ice cream, but a chocolate scoop of ice cream is different than a strawberry scoop of ice cream. Both ice cream, different flavors. All atoms, different flavors of matter, elements. And so we depict these, because you can't see them with the naked eye, as these little balls. And we put those balls together, either smash them together, as we see here over here on the right, or we connect them with these little sticks that represent the bonds between them, which we'll talk about a little bit later. And then the colors of those balls indicate that there are different flavors, that there are different elements. Right? Now, if we want a menu of all the different flavors, we can look at the periodic table. And we'll come back to the periodic table, but this is jam-packed full of information, just a ton of stuff here. This is going to list all 92 naturally occurring elements, as well as all the synthesized elements that we've been able to create in the lab. But you're going to see this again and again, and you're going to use it a bunch in the future. Now, if we look at an atom, again, this is pretty basic stuff. If we look at an atom, we have to understand the components of an atom itself to understand why atoms do what they do. And that's going to be really important as we get into biochemistry. And we already know that we have to understand the chemistry well to understand the biology well. So one thing that's going to happen here is we're going to use words that have different meanings depending on what field you're talking about. So especially when you're talking about science, there are oftentimes words that we use in everyday language that we use in science, and they mean something different in the context of science. When we talk about the nucleus here in chemistry, for example, we're talking about the nucleus of an atom, and this is where we see protons and neutrons. These are two subatomic particles. The nucleus of the atom is then surrounded by orbiting electrons in specific shells. Okay, so think about them as orbits around the atom, and those are three subatomic particles: electrons, protons, and neutrons. Now, when we talk about the nucleus, again, in chemistry, I'm talking about the nucleus of the atom. For most of this quarter, we're going to talk about the nucleus of a cell, which is actually an organelle, a small compartment in a eukaryotic cell that contains the DNA. Same word, two very different meanings. So let's keep that in mind as we move forward. Again, our three subatomic particles that I need you to know are the electron, the proton, and the neutron. Now, what's super important in this crash course in chemistry here is that it's about the charge, right? Electrons have a negative charge and protons have a positive charge. When we look at the breakdown of a particular element on a periodic table, we can see, we're zooming on one of the little boxes, right? So you have usually the name of the element at the top. That's the flavor, right? The atomic number. Now, this is where the charges come into play. So the atomic number is the number of protons in the nucleus of that particular element. And that is what dictates what the element is. All right? So only carbon will have 6 protons in its nucleus. If it has fewer or greater, it's a different element. All right? Now, in its natural state, carbon is going to have 6 protons, each having a +1 charge. Hence, it will also have 6 electrons that each have a -1 charge, and those charges then cancel each other out. So an atom in its natural state, kind of base state, is going to have a neutral charge. Now, the number of protons dictates the number of electrons, and then what we're going to see is that those electrons and how they orbit or how they circle around the nucleus is really going to indicate how it reacts with other kinds of things. And that's chemistry, right? So what we can see also on this little square is the atomic weight. Now remember, we've been focusing on electrons and protons, but there's also this third subatomic particle called neutrons the neutron, is in the nucleus as well. It has no charge, so it doesn't play a huge role in the chemistry of the element, but it is going to play a role in creating what we call isotopes. All right, before we go there, though, let's just review. Atoms of various elements have differ in their number of subatomic particles, specifically the protons, right? So an atom's atomic number is the number of protons in its nucleus. That's what gives its defining characteristic. We can add the protons plus the neutrons and get the mass number, and if we add all the electrons as well, we get the atomic mass. That tends to be a very small difference than the mass number, because the electrons are have such small mass, as you can see there. Now, the reason we bring up neutrons at all is because they're going to be the source of isotopes. So carbon has 6 protons. Every atom of carbon has 6 protons, but it may vary in its number of neutrons. And when we have variation in those neutrons, those different atoms with different numbers of neutrons are called isotopes of each other. Why do we care about that in biology? Well, because many of those isotopes are radioactive. As you load up the nucleus with electrons, what you tend to get is instability. And that instability then can result in the spontaneous decay of that nucleus, and that gives off energy. Again, why do we care in biology? You've got plenty of isotopes in your body right now, and that's not a problem. That's a normal thing. But what we find is that for nuclear medicine, when we want to do lots of imaging, when we want to detect things at very, very small concentrations, the energy that those isotopes give off is very easy to see. Or it's we can make something very, very sensitive if we use radioactive isotopes in our assays. So we're going to talk about these more later, and I want you to have that basic foundation of where they're coming from and what they are. So for example, like we used to use tritium all the time in the lab to label our proteins. And so tritium is hydrogen, but it's hydrogen with 2 extra protons in it. So this now is an unstable molecule, and it gives off a very, very tiny amount of energy, but that's energy then that I can detect, and I can follow very, very small numbers of molecules through the cell or through an assay. So helium, lithium, you can see when you have, again, a different number of neutrons, you get an isotope. Right? Now, speaking of biology, we want to focus on the elements that are most abundant in biological systems. And this chart here gives you a great summary here. Now, HONC, these top 4, H, O, and C, hydrogen, oxygen, carbon, nitrogen, are going to be our most abundant. 96% of the human body is HONC, which is the case for most organic matter. And then we have calcium, phosphorus, potassium, sulfur, sodium, chlorine, and magnesium. You just need to memorize these and have them in your head. HONC is easy because it kind of makes a word. This is also going to have a role later when we start to think about bonding properties, where hydrogen wants to make 1 bond, oxygen 2, nitrogen 3, and carbon 4. So 1, 2, 3, 4. That's easy. And then you're going to have to come up with some way to remember these. So calcium, phosphorus, potassium, sulfur, sodium, chloride, and then magnesium. It'll get easier as we go, as you study more, because you're going to see these again and again and again, but what you have to do is see them. So I want you to get them in your head so that when we talk about a calcium pulse as a intracellular signal, it's not so foreign. It's like, what is that CA you're talking about? It's calcium. All right, so get those in your head. Now, there's a lot of elements on the periodic table that we're not going to deal with in a biological system. What we're going to see is that those most abundant ones are going to kind of cluster over here and over here. And as you take more chemistry, and you should take as much chemistry as you can, you'll understand better why that is. But for now, we're going to charge on and kind of consider the properties of these elements when we start to talk about bonding in our next recording. So again, if we look at this, what we want to start to think about is the final structure of the atom, and that is, again, the nucleus with these orbiting electrons, right? And so the thing about those orbiting electrons is they are orbiting the nucleus in very distinct patterns. We call them shells. And really, they're moving so very fast that it's almost a cloud. These depictions, though, of electrons around the nucleus are very easy to understand and see, and they're going to be very applicable for our understanding of the chemistry that's going to go on. But you can see hydrogen is just a single proton for its nucleus and one electron. It has room for one more electron in that first shell. Whereas if you look at carbon, carbon's got 6 protons in the nucleus, and then 1, 2, 3, 4, 5, 6 electrons total, but 4 of those electrons are in the outer shell, and it has room for 4 more electrons. And that's going to come into play as we move into bonding. But again, we want to remember that electrons are negatively charged and protons are positively charged, and therefore you're always going to balance each other out. Right? Now, again, the way those electrons surround the nucleus, like we talk about them as electron clouds, they do have different shapes, these orbitals. We're not going to worry about that too much for this class, but that is going to come into play later when you talk about the difference between sigma bonds and pi bonds and how organic molecules get together and have the characteristics they do. But you'll cover that more when you take chemistry and organic chemistry. All right? So for now, remember the structure of the atom, what are elements, protons, neutrons, electrons, charges of each, and you'll be fine.